Okay, so this is the second of our lectures on the class review. And today we're going to start out with software-defined storage. And we're going to start thinking about some of the advanced stuff that companies are looking for from their storage architectures. So software-defined storage is a way to to organize storage architectures in a way that's disaggregated, policy-based, automated, incremental, commodity-based, pooled, self-service, all that kind of stuff. Those good things that uh, build flexibility into storage environments that companies are really looking for. Flexibility as well as auditability. That's the automated and policy-based kind of stuff. So, what's the value of software-defined storage? Well, how can we use software-defined storage to deliver this value? Where does the software in storage come into play? So you get a flexible construction of services where we have software-defined storage spanning the boundaries between servers and storage. So instead of managing individual storage servers, we manage a pool of storage in a way that can span those different servers. If you have, 50 gigs on this machine and 10 gigs on this other, then you're not managing one that's big and one that's small. What you're managing is a pool of 60 gigs of storage, and it doesn't really matter which server that storage is located on. So if you had, one server that needed 12 gigs, it could span the 10 gig server and then onto the 40 gig server. So that's a really powerful capability for companies, and it's something that they're really interested in because in the past we had these isolated spots of storage, and so and a great way to crash a server was for the server's storage array to become full and have no room to put anything. What would the server do? And just give up the ghost and crash. And so having pools of storage to work with gets around all those old issues. Huge deal. So let's see. And this has potential impacts on security and availability, of course, is part of security. And servers crashing because they run out of storage, that's against availability. And then reliability. So rather than have all of the storage associated with an application be on one single device, which of course can fail and will fail, we spread that storage across multiple devices and in such a way that the failure of any single device doesn't mean the failure of the application. We separate control and data planes. So data planes, that's where you actually store the physical bits. The control planes can be someplace else. And that helps out because it makes it so the control planes can be more sophisticated and can control lots of data planes located, around the world. So software-defined storage builds on virtualization of the data path. So the data path, the application thinks that it knows where the data is being stored, but in fact it doesn't. It gets virtualized. It gets sent all over the place. And then deployment simplicity, where we get, let's see, express requires, okay. And let's see, so storage service interface means that we can build a better interface between the storage bits and bytes and the requirements of the application. And that deployment simplicity, that's huge. That's what companies want. Now, we're talking about a couple of different file systems in this class. We have ZFS that you guys do the one lab with the EasyNAS, and then we're going to talk about Gluster, and I can't remember what else we talked about. But anyhow, we'll get there. So ZFS is really interesting because it's one of these things that it's a service that pools storage arrays. So if you look at the traditional architecture where we have partitioned volumes per file system, we have fragmented capacity and I/O bandwidth, manual resizing, and growing storage. If you have three servers that have 10 gigs apiece and you need 12 gigs, then you're mixing and matching stuff, and that's a problem. Also, if you allocate applications to individual storage arrays, then you are tied to the performance that exists only with the net storage array. That's a problem. But Z doesn't do that. Z allows us to avoid having these partitions, and the assignment of the total storage to file systems is flexible. So if you've got three 10-gig disks, you can assign 12 gigs to one application, and 5 gigs to another, and whatever else to a third. And that makes things a lot more flexible, a lot more useful, and makes it easier to organize things. Integrated error checking, that's a really important thing too, because it means that you can check for errors in the way that the disks degrade, because over time disks always degrade, and they degrade by ones becoming zeros and zeros becoming ones. And if you do integrated error checking, that provides a way for you to check to see if those ones are degrading in a way that's unacceptable or not. It allows snapshots, clones, compression, deduplication, all that kind of good stuff within Z itself, rather than making it that part of an application someplace. So this is another example of abstraction where Z takes all those requirements away so that the operating system doesn't know anything about them and doesn't need to. Yeah, and so that's kind of where Z comes in for us. It also has this notion of copy on write transactional file system. So if you start with a consistent state where we got two servers down there, and then we've got a processing head end, and I can't remember what the last bit there is called, but then you go to write some files, then the disks that you write to are now out of the metadata is written to the storage server on the top there, and the Uber block is that top device. That Uber block contains a hash value for the entire consistent state. There we go. So if we go to number 2, where we write some data to these files, then we're no longer in a consistent state. So the disks on that left side of the drawing then recalculate their hash value and then push that hash value up to the managing box on top there. And then the Uber block writes all of that stuff again. And when the Uber block writes it, that's like a commit. And the data is now committed, and we're back to a new consistent state again. So this copy and write is kind of complicated, but if you spend a little bit of time reading about it, it's a neat idea because it gets at this ability to use hashes to keep track of the status of file systems. So Gluster is another file system that we're using. And Gloucester has a bunch of features that is really kind of cool. This global namespace, so that means, which is a lot like Amazon's S3 environment, it has a global namespace also. And what that means in this environment as well as in Amazon is that you have an account, and in that account you have a namespace. And of course the accounts are unique across all of Amazon or Gluster, and that means that everything inside those accounts is unique. So I might have a file in my account CBBICS that's budget, and then somebody else could have another, it could have another account name, and inside their account name, they could have a file named budget. But it still is a globally unique namespace because of the difference in the account names. Clustered storage, we take lots of devices, bring them all together. Modular and stackable, highly available. We got built-in replication, and then geo-replication. Geo-replication is the idea that instead of just saying, if you've got a global storage environment, when you replicate a file, you don't want it to save that replicated version on the same server as the first version. What you want to do is you want to push it out someplace. And that out someplace could be locally in the same environment, or it could be a geo-replication where it's out in a different part of the world. Now, the reason you want to do that is because that gets you out of these disaster zones, and by being in a different zone, then you're not going to be subject to the same set of natural disasters. Self-healing, that means that it rebuilds itself continually, which is really nice. NTFS does this also, so that even if you don't access a file, NTFS will look at it, make sure that the bits make sense, that the CRC that's calculated makes sense, that the hash makes sense, and if the hash still works, it just keeps on copying itself. The hash doesn't work quite right. It has enough information, kind of like parity information, to go back and rebuild the file to make it so that it works. Then the ability to rebalance data. So if this disk is filling up, it can move it onto another disk. Gluster terminology. All right, so you got four main concepts in Gluster. One first concept is bricks. Bricks are kind of like disks themselves. So storage units, which consist of a server and data path and directory path. So on this server, this disk. Translators are modules that are chained together to move data from point A to point B. So translators are data movers. They move data from one device to another. Then you have trusted storage pools, where you have a trusted network of servers that will host storage resources. Now, by trusted, we mean it's under our control. And things that are under our control, we trust. If it was in somebody else's environment, then it would be an untrusted storage pool. And then volumes, which are a collection of bricks with common redundancy requirements. Bricks, multiple bricks create volumes. Multiple volumes create trusted storage pools. Translators are not part of that hierarchy, but they're part of the overall scheme of things in Gluster. So, all right, trusted storage pools contain one or more storage servers that will host Gluster volumes. A brick contains the name of a trusted storage server and a directory on the server where data will be read and written by clients. Bricks are combined into volumes based on performance reliability, and volumes are shared with Gluster clients through CIFS, NFS, or the Gluster file system. So, kind of what I said last time, but that's the way it goes. Gluster volume types. So we can have a number of different volume types in Gluster. We can have distributed volumes, we can have replicated volumes, we can have striped, we have distributed replicated, and distributed striped. Okay, so that's Z in Gluster in a really short amount of time. I encourage you to spend probably more time on Gluster. I think Gluster is a more useful technology, since it's been picked up by Red Hat and of course now IBM. That means that you're going to see a lot more Gluster around in industry accounts because they're either from their Red Hat days or from their IBM days. But anyhow, so Gluster is a really useful technology to keep track of. So another topic that we talked about in this class was backups. And backups sound really boring, right? But in fact, backups are really complicated, and it's one of those areas where if you are involved in systems at all, where you can get yourself into big, big, big trouble because people just expect backups to work, and they don't realize how complex they are. And so, spending time on practicing backups and restores is crucial. If you're charged with dealing with backups and you don't get extra hardware to practice with and extra time to practice backups and restores, then it's time for a new job because they're not supporting you in a way that will make you efficient and effective. And then the time's going to come and you're going to screw it up because you won't have practiced. So backups are complicated. So the architecture that most big scale backups have is you've got you've got clients out there, and then you've got servers, and the servers are backup clients. Then what we really want to do is we want to back up those servers, create copies of those servers onto a backup server that also has a storage node. Okay. Now the important part of this thing is that in this drawing is that we've got our tape backup machine, but next door to that, we've got our metadata catalog. And that metadata catalog is data about the data about backups. So, if you lose your metadata catalog, you pretty much don't have a useful backup set. So the metadata catalog is really complicated because even in the best of scenarios, it can be people don't think about creating multiple copies of it and backing up the metadata server. And so if that's lost, then you really don't know where your files are. And let's see, so what else we got? Okay, so we've got a couple of different requirements around backups, which makes it really hard. You've got the day-to-day backups and recoveries, right? Somebody's working on a file, they screw it up or lose it or whatever, and they call you during the middle of the day and say, can you restore, budget.xls? Say, okay, fine. You go to the metadata catalog, look in the metadata catalog to find the data set that file is part of from last night. Then you go through the metadata catalog. It accesses the tape backup or the disk backup. And if it's from last night, it's probably on a disk backup. And then gets the old copy of it, and it allows you to forward it out to the person who requested it. So that's just operational backup and recovery. But then you also have the the weekly backup and recoveries that people do, and that's a different class of stuff because not only do you have that metadata catalog which keeps track of where these files are located, but the files are going to be put onto a tape or onto some longer term backup environment, and that's going to be a lot slower for you to access. So that's a different kind of scale of things. And then in that requirement, you also have all the production backups that you need. And these are things like monthly backups and the month backups of all your accounting data, the quarterly backups of all the accounting data again, and then the annual backups that are accounting data again. So backups and accounting go together like peas and carrots. And so there's a lot of different tasks around that. And then even after that, so if you do an annual backup, usually you'll take a snapshot of the books of the company at the end of the fiscal year, and that end of fiscal year uh, picture of the data is then stored in a read-only location, so that people can look at it and they can't change it because that's what the accounting system looked like on December 31st at midnight. And then after that, you also have another whole nother class of backups that are the archives, so that you're not only going to want to save that image of the snapshot of the books on December 31st, but you're going to want to have years and years and years and years of that going backwards too. And those are archives, and archival storage is different than tapes, because not only is it all read only, but it's big and it goes back a long ways. So, usually you'll have a separate a separate location to store your archival backups to also. So backups are really important. They're hard to do well, and they need a lot of time and babysitting to make sure that they happen on whatever basis you're looking for. And then the last thing that we talked about in this class is this whole notion of disaster recovery and business impact analysis. And it's a fun lecture for me because I get to show lots of pictures of disasters, floods and earthquakes and lightning strikes and all that kind of good stuff. But what it all boils down to is this notion of business impact analysis, which is it, the threat and attack identification and prioritization, uh, thinking about what the potential damage is for all the different threats, and then coming up with a way to deal with that through both an incident response plan, disaster recovery plan, and a business continuity plan. And by the way, those are all different. Incident response is what do you do right away? Okay, how do you get from an incident plan to an incident detection to an incident reaction to an incident recovery? Now, I stopped at incident detection because that's a really complicated thing to have happen. Because when you think about it, bad things happen all the time, but some of them we declare incidents and we respond to them very aggressively. Others are just normal stuff. Depending on the size of your business, somebody, crashing a car into your one of the locations, that's not an incident. That's just normal stuff. Um, but if you have a big, and if you have an ice storm and a power outage in one location, that may just be something that you just roll with every day. But if you're a little bit smaller, losing a location can be a big deal. But the big question that you have around incidents is who declares them? Who's empowered to say that now this is an incident? We're going to go into our incident response plan. We're going to, declare a disaster. We're going to move on, blah, blah, blah. Um, Mostly because when there is a disaster or an incident, uh, there's a whole bunch of budget lines that get freed up. Before your company may have had a working plan that was no overtime, nobody ever gets overtime, no way, no how. Well, all of a sudden, a disaster happens, an incident happens, and guess what? Everybody's on overtime. So who's the one who makes that, who goes from normal business operations to disaster recovery operations? Somebody has to do that. And the problem is that somebody can needs to be somebody pretty senior, but they need to be somebody that's around. So you can't just have one person because your senior people usually travel quite a bit. And not only do you have to have multiple people authorized to do this, but you have to be able to contact them, which means private cell phone numbers for your CEO that exists in the data center. You know, who keeps track of that? Your CEO, if they aren't very enlightened about this, may say, "No way, that's my private number." Well, you know what? We need to get a hold of you if we have a problem in the data center. And so, it's those kind of things that make disaster recovery planning so difficult. because it can be so wide ranging across the impact of a disaster can be wide ranging across your organization. And, to make this all work together is very complex. And so that's what I really wanted you to get out of this business impact analysis, and is a way to think about the big scale things that big organizations need to think about and have plans in place for. So somebody's job has to be to think of everything bad that can happen to your company and then decide which ones of those bad things are more likely to happen than other ones so that you can plan and how to respond to those bad things that are bad and you think will happen. But the bad things that are bad and things you don't think are going to happen, those, you don't need to worry about so much. But so, anyhow, that's what I was thinking about with this business impact analysis, disaster recovery. You should have all the slides for that, including all the pictures of the floods and everything. So I hope this helps. I'll get in touch with you guys and talk to you about what's going on, and we'll go from there. So take care.